Okay, so let's now talk about the second example of a very important avenue where we can talk about the game and where we will analyze the efficiency of the stable state, namely of Nash equilibria. Actually, it's the first example in the sense that the previous example about routing was not formally a game in the formalism that we had introduced in the beginning of the course. So this example and all the other examples we will see today, actually they are proper games. So the number of players is finite. It will be exactly games. These will be exactly games as we introduced in the beginning of the course. So this example is about network design. So unlike routing, when you have a network and you ask about how something can be routed, excuse me, now how something can be routed in that network, here you have certain goals, connectivity goals to be precise, and you ask about what edges shall you utilize in order to fulfill those connectivity goals. So basically, that's another look on a similar topic of connecting stuff and routing stuff, of course. But here you are talking about connectivity load. So just connect stuff. Of course, later it can be useful routing whatever. So formally, this problem is called Shapley network because the division of the cost will be related to Shapley value, but that's something we don't study at this course, and you don't have to know that. So just that's called Shapley network. Shapley was a very famous scientist in game theory, in combinatorics and algorithms. So that's yet another place where his name appears. So Shapley network design game consists of, and as I also kind of hinted, the network design games are basically a group of games. It's a huge set of games. And now so we are studying a concrete simple case called Shapley network design game, which has a directed graph on vertices V with the arcs E. Perhaps I should have denoted it by A because these are arcs, not just undirected edges, but they are directed. Every directed edge, well, when I say edge, I mean an arc in the sense of a directed edge. Every directed edge here is endowed with a fixed cost. Unlike what we saw in the routing case, here the costs are fixed. And the question is not what is going to be the cost because they're fixed. The question is which edge will be used, and if yes, by whom, and then the cost is divided, but the cost itself is fixed. And the players, there's a finite number of players, k, so it's a game, proper game. Each player is endowed with the source and the destination. The source and the destination of player I are denoted by Si and Ti, respectively. These are just some distinct nodes in this graph. Of course, different players may have the same, they happen to have the same sources or the same destination. So the source of one player can be the destination of another player. So there is no rules about that. Simply each player is endowed with a source and a destination. And now player I needs to connect its source with its destination by a directed path from S to T, from Si to Ti, by a path Ti, which can be seen as a set of edges. And the strategy of a player is choosing a path from its source to destination among the set of all the existing paths. And we assume that each player has at least one such path. And then the cost, it's a cost minimization game, the cost of player I is her fair share of the total cost. Formally, the cost of player I is the sum of the costs of her shares for each of the edges in the path she uses, when we look at the path as a set of edges. And what is that fair share? It's simply her share of the total cost, so CE divided by FE, where FE is the number of players using that edge. formally, F is the cardinality of the set of all the players J whose path contain that edge. So I look at all the players who have chosen a path containing that edge, and then I look how many such players exist, and then I divide the cost of the edge by the number of players who have chosen to use that edge. At least one player has, because I'm looking at a player who uses that edge. So at least one, it's well defined. And then I just assign the player to pay that share cost for each such edge. So each edge that player uses, how many others use that edge? Let's divide the cost of that by the number of users. That's what the player pays for that edge. And going on for each of the edges the player uses. An example, a simple example, when you have a graph from S to T, you have K players. Each one of them has the same source S, and they shall also share the destination T, and each one has just to connect them. So you have two paths from S to T. They're just very simple. One path, it contains one edge, which costs K, the upper edge in the picture. And the other path contains one edge, which costs 1 plus epsilon for small enough epsilon. Small enough means that for all the needs we may have, it's small enough to satisfy those needs. And then we consider those K players. Now, consider the step, before we go on. So what we've defined is a game. The players 1 to K. The strategies are those paths. Each player chooses a path. So all the strategies of player I are all the paths in the graph from Si to Ti. And the cost, I've defined the cost, the sum of the cost of each of the edges. So that's a game. Now, a social optimum profile. Strategy profile is basically a profile of which path each player chooses. A socially optimum profile is that for each player, she chooses the path below, and then the total cost is going to be 1 plus epsilon. Otherwise, the cost is going to be at least K, and since epsilon is small enough for any K, which is at least 2, because it's better to choose the lower edge for everyone. So that's the social optimum profile. That's also a Nash equilibrium, because given that profile, of course, no player would like to deviate and play K instead of paying 1K of 1 plus epsilon, which is approximately 1 over K. So there is a socially optimum Nash equilibrium, therefore the price of stability is 1. Now, is that the worst possible Nash equilibrium? You may stop the video and think, and the answer is no. So there is another equilibrium where everyone chooses the upper path, and that's actually the worst equilibrium. That's the only one equilibrium. So the only one other equilibrium we have here. And here now I'll prove why it's the only one equilibrium besides. So there is no equilibrium when some choose the upper edge and some others choose the lower edge. But before that, let's just ensure they understand why this is an equilibrium. When everyone chooses the upper edge, everyone pays K, the cost of the upper edge, divided by the number of players who have chosen that edge, which is also K. So everyone pays exactly 1, and unilaterally deviating to the lower edge would make that deviator pay 1 plus epsilon. And however small that epsilon is, it's still a positive number. So if someone deviated there, he still would pay more than 1, which is still worse than paying K over K, which is exactly 1. So that is a Nash equilibrium, and that's of course the that's now we prove that that is the only one, and therefore it's the worst equilibrium, because one could actually use what if some use the upper edge and some use the lower edge, and then the total cost is K plus 1 plus epsilon. Then that would be the worst. that's not that's not an equilibrium, because if both edges are used in an Nash equilibrium, then what it means that this is a Nash equilibrium, it means that the lower part, those who use the upper edge, they pay k divided by the number of those who use the upper edge, I denote by f with the subscript u. That cannot be more than what a deviator would pay if he deviated to the lower edge, because that's an equilibrium. Now, what would he pay if he deviated to the lower edge? He would pay 1 plus epsilon divided by the number of users of the lower edge plus 1, because that deviator would have been added to the number of users. And therefore, this condition of equilibrium, that's only part of the condition, of course, because another condition is that the users of the lower edge don't want to deviate. But already that condition implies that k divided by f u plus 1, so I make the denominator larger, and therefore the whole expression becomes smaller. Now it's strictly smaller than 1 plus epsilon divided by fl, and here I made the denominator smaller, and thereby the whole expression becomes strictly greater. So I just made the left hand side strictly smaller, the right hand side strictly greater, and therefore the weak inequality has turned to a strong one. And that new condition, what does that imply? So think, maybe stop the video. What that implies is that in the current profile, any user of the lower edge would strictly benefit from deviating to the upper one, because any user of the lower edge now pays exactly 1 plus epsilon divided by the number of the users of the lower edge, I denote by fl. That's the right hand side. That's what any user of the lower edge pays now. If she deviated to the upper edge, what would she pay? She would pay the cost of the upper edge, which is k, divided by the new number of users of the upper edge, which is the previous number of users, fu, plus that deviator, plus 1. And since we have just concluded that that expression that is strictly smaller than what 1 plus epsilon divided by fl than what she paid before is, that means that that deviation would have paid off. And that contradicts the assumption that it's a Nash equilibrium. So indeed, there is no Nash equilibrium where some users use the upper edge and some users use the lower edge. And they have to either, all of them have to use the upper edge or the lower edge. So there are exactly two equilibrium. One is when everyone uses the lower edge and then the total cost is 1 over epsilon. The other one is when everyone uses the upper edge, and then the total cost is k. And the lower, the cost equilibrium has to be also the social optimum profile, and the price of anarchy is k, the cost of the worst equilibrium divided by the social optimum, 1 plus epsilon. So we have seen here an example where the price of stability is 1, whereas the price of anarchy is k divided by 1 plus epsilon, which for small enough epsilon is very close to k. So there is a huge gap, approximately the number of players, between the price of anarchy and stability. That's an example where some regulation, some hinting to do something which is profitable, namely to use the lower edge, would be really instrumental. Now the question is, but is the price of anarchy always 1? Is the best equilibrium always optimum, or are there cases where even the best equilibrium is far from optimal, or at least non-optimal? And the answer is no, it's not always 1. So now we look at a very cute example where the price of anarchy is actually not 1. So, okay, so 1 second, yes. So this is an example which actually is of a non-1 profitability. So we have n players here, 1 to k. Player I has the source Si, S1, S2, and so on till Sk, and they all share the sink or the target, in other words, T, the common target T. Now the costs are drawn, and each player faces the choice between two optional paths from the source to the target. So one path is, let's say, player 2, from S2 to V, that edge costs 0 and can be used only by the player, and then from V to T by the common edge from V to T, which costs, the edge costs in total 1 plus epsilon, and depending on how many share that edge, that will be the cost 1 plus epsilon divided by the number of those who share that edge. Another path is simply to go directly, and for player I, it costs 1 over I. For player 2, it costs 1 over 2, and in general, it costs 1 over I. For player K, it costs respectively 1 over K. So there are two paths for each player. And so in the optimal profile, each player pays 1 over K from the 1 plus epsilon. The K share of 1 plus epsilon, so everyone plays the path from Si to V, and then goes from V to T. In total, that costs 1 plus epsilon. That's definitely the socially optimal way, because all the other ways, which have a chance to be better, don't use that edge at all. I mean, better in the sense of the social cost. And then if you just sum up all the costs that you pay, it's 1 plus half plus and so on. And for small enough epsilon, already 1 plus half is larger than 1 plus epsilon. And therefore, that's the optimal profile. And the social cost is 1 plus epsilon, the total cost. Now, that's not Nash equilibrium, unfortunately, because for the last player, what happens is that that player faces the choice, as every other player, whether to play through V or to go directly to T. Now, the direct path costs 1 over epsilon, and going to V and then to T costs, in the best case, if everyone else uses Vt, as well, it costs 1 plus epsilon over K. So strictly more than just going directly from Sk to T. So for player K, choosing the direct path is strictly dominant. Yes. Excuse me for the confusion with the with the browser. So strictly dominant. Now we can delete the other strategy, which is strictly dominated. And in the sub game, then the next player we look at is the player K minus 1. And in the sub game, of course, going directly will be strictly dominant for that player. It was not strictly dominant in the beginning, because 1 over K minus 1, 1 over K minus 1 does not necessarily give us is not necessarily a smaller cost than 1 plus epsilon divided by K. But it is always a smaller cost than 1 plus epsilon divided by K minus 1. Now, having deleted the strategy of player K that goes through V. And then we continue that way in vectoring, and we delete all we successively delete all the strictly dominant strategies. And in the beginning, we only have the strictly dominated strategy. Strictly dominated strategy. In the beginning, we only have the only player K has a strictly dominated strategy to delete. But after deletion, player K minus 1 obtains the strictly dominated strategy, in the sense that one of his strategies becomes strictly dominated, and so on till in the end, the game is only left with every player is only left with one choice, and that's going directly. So player I goes from Si to T directly, and That's known in Nash equilibrium, as you know, and that equilibrium is that everyone goes directly. This costs, how much does it cost? 1. So player 1 pays 1, player 2 pays 1 over 2, and so on till player k who pays 1 over k. It basically is the sum of 1 over I for I from 1 to k. And that costs approximately logarithm. So the price of stability is this sum, it's called the Cave harmonic number, divided by the optimum, which, as we have mentioned, is 1 plus epsilon. Everyone just goes through v. So that's approximately logarithm when epsilon is so very small. So here the best equilibrium is already quite far. The optimum. And then the natural questions are, so first, does every Chaplin network design game does every such game possess a pure equilibrium at all? Because we assume there is such an equilibrium, at least in our cases, indeed there was such an equilibrium, but is that true for every such game? Otherwise, the question about efficiency don't make sense. We can speak about the efficiency mixed extension of the game, and being a finite game, this game definitely, in the mixed extension, there is definitely at least one equilibrium. But the pure game may have no equilibrium, and then there is no sense to talk about efficiency. Then the question is, okay, if there are games where the best equilibrium, namely the price of stability, already is quite high, or the best equilibrium is already quite bad relative to the optimum social welfare, what is the largest price of stability in such a game, in Chaplin network design game? What is the, so basically, what is the game where the equilibrium, the best equilibrium, is the worst possible among such games? And the answers, which we don't prove now, but we will, is that first of all, the set of Nash equilibria is always non-empty here. Second, the largest price of stability, so the worst case, in this sense, for a Chaplin network design game, scale players, is actually attained in the example we've just seen. That's the sum of 1 over I, from y going from 1 to k. That's the harmonic number. And that's something we still need to prove. Okay.